Welcome to this lecture on ordinary differential equations. Today, we are going to explore a fascinating and powerful mathematical tool called the Wronskian. When we solve complex differential equations, we often find multiple solutions. But how do we know if they are truly unique? The Wronskian acts as a mathematical lie detector, telling us instantly if our solutions are independent or just lazy copies of one another. Let us dive in and see how it works. Now that we know what we are looking for, let us start with a simple analogy. Imagine you hire two detectives to investigate a complex mystery. If the second detective simply follows the first one around and copies their notes, having two detectives gives you absolutely no new information. In this scenario, the detectives are dependent on each other. In the world of differential equations, we often need two separate mathematical solutions to fully describe a physical system. If one solution is just a scaled-up copy of the other, it is useless to us. We need a way to verify that our solutions bring genuinely different information to the table. This brings us to the formal mathematical concept of linear independence. In formal mathematics, we use the term linear independence to describe functions that are fundamentally different from one another. To put it in the simplest possible terms, two functions are linearly independent if you cannot multiply one of them by a plain number to magically create the other. The Wronskian, named after the brilliant mathematician Joseph Maria Wronski, is a special mathematical tool called a determinant, used to test this exact property. If the final expression we calculate is anything other than zero, the functions are officially independent and can be combined to form a complete general solution. Now that we understand what the Wronskian does, let us look at how it is mathematically structured. This formula shows the initial setup for calculating the Wronskian of two functions. The abbreviation DET stands for determinant, which tells us we need to perform a specific cross multiplication on this 2 by 2 grid. We place the original functions y1 and y2 in the top row. Directly below them, in the bottom row, we place their corresponding first derivatives, y1 prime and y2 prime. These derivatives show how fast each function is changing. This grid organizes our information perfectly for the next step. Building on our determinant grid, we can now expand it into a ready-to-use equation. We perform the determinant cross-multiplication by multiplying the top left function, y1, by the bottom right derivative, y2 prime. Then, we multiply the top right function, y2, by the bottom left derivative, y1 prime. Finally, we subtract the second product from the first product to get our final result, denoted by the capital letter W. If the resulting value of W is not equal to 0, it mathematically guarantees that our two original functions are linearly independent. If it equals 0, they are dependent. To make this formula easier to remember, let us visualize the cross-multiplication process. Here you can see the determinant grid we just discussed. The solid blue arrow represents the first positive multiplication step, connecting the top left function to the bottom right derivative. The red dashed arrow represents the second multiplication step, which is always subtracted from the first. By memorizing this simple visual cross pattern, you can easily construct the Wronskian formula for any pair of functions without having to look it up in a textbook. This visual trick will save you a lot of time during exams. Before we move on, let us see this formula in action with a concrete example. We are given two mathematical functions, a standard cosine wave and a standard sine wave, and we need to determine if they are linearly independent. These commonly appear in oscillating systems like pendulums. We begin by assigning the cosine function to y1. Using basic calculus, its first derivative, y1 prime, is negative sine of t. Next, we assign the sine function to y2. Its derivative, y2 prime, is positive cosine of t. We now have all four pieces needed for our determinant grid. Now that we have our four components, let us plug them into the expanded Wronskian formula. We multiply cosine by cosine and subtract the product of sine and negative sign. Notice how we carefully track the negative signs. Multiplying these out gives us cosine squared minus negative sine squared, which becomes cosine squared plus sine squared. This leaves us with a very famous trigonometric identity. Using the fundamental Pythagorean identity, we know this always equals exactly 1. Because 1 is clearly not equal to 0, this physically and mathematically proves that the sine and cosine functions are completely linearly independent. Let us look at another scenario where the functions might not be as helpful. We are given a first function which is an exponential growth curve e to the power of 2t. We assign this to y1. Using the chain rule, its derivative, y1 prime, is 2 times e to the 2t. Our second function is simply 5 times that same exponential growth curve, which we assign to y2. Taking its derivative, the 2 comes down and multiplies by the 5, giving us y2 prime equals 10 times e to the 2t. Continuing with our exponential functions, we substitute all 4 expressions into the Wronskian formula. The first half multiplies e to the 2t by 10 e to the 2t. The second half multiplies 5 e to the 2t by 2 e to the 2t. When we multiply matching bases, we add their exponents. Both products simplify to exactly 10 times the exponential of 4t. We are left subtracting a value from an identical value, so the entire expression completely cancels out. The final result is exactly 0. This mathematical 0 acts as an alarm bell, telling us the functions are redundant and dependent. Now that we have calculated the Wronskian manually, let us look at a powerful shortcut known as Abel's theorem. This remarkable formula represents the Wronskian as a function of time. The symbol c is just a constant number, determined by the initial state of the system. The symbol p of t comes directly from the middle term of the standard second-order differential equation we are trying to solve. Because the mathematical constant e raised to any power can never equal exactly 0, the exponential part of this formula is always strictly positive or strictly negative. Therefore, this theorem proves that the Wronskian is either 0 everywhere or 0 nowhere. You might be wondering why we care so much about this lie detector test. Understanding the Wronskian is absolutely critical when engineers and physicists build mathematical models of the real world. A second-order differential equation often describes complex physical systems that vibrate or oscillate, such as a skyscraper swaying in the wind or an electrical circuit processing a radio signal. These physical systems always require 2 independent pieces of initial information to predict their future behavior, such as starting position and velocity. The Wronskian guarantees that we have captured the full, complete behavior of the physical system, ensuring our model will not fail when we actually build the real bridge or circuit. We have covered a lot of ground today, so let us summarize the most important ideas. First, the Wronskian is a highly effective mathematical test used to determine if multiple solutions to a differential equation are truly unique. By arranging functions and their derivatives into a determinant grid and cross-multiplying, we generate a single expression. A non-zero result confirms that the functions are linearly independent and can form a complete general solution. Conversely, a result of exactly 0 warns us that the functions are dependent. Finally, Abel's theorem provides a powerful shortcut, proving the Wronskian is either 0 everywhere or nowhere. You now have the tools to confidently analyze differential solutions.